All right, welcome to again, Maths 2504 for Monday. Hello. Okay. So 5 o'clock, we'll get started. Maths 2504. We're up to week 4. I think that sounds a bit loud. Yes. Okay. All right. So, okay, week 4. All right. So this week, we're going to try and finish out Unit 2. Hopefully this lecture I'll start on Unit 3 because it's another bit, not getting much more time for my stuff. You've only got like 3 more lectures with me, so 5 hours total. Big lot the week 2 weeks after. Homework will be due the week after that, and then quiz the week after that. So, and after me, you'll have Andy, and he'll go through a bit more about, hopefully a really valuable one for you guys, because he'll go through a bit more about type system in Julia and a bit more into the guts of, you know, how the type system works, which will be, didn't want to overload you early on, get a nice introduction from Andy. Andy is an expert at that stuff as well, so best person to be teaching it, I think. Okay, hope you all enjoyed Megan coming in last Tuesday. Really cool to see all the questions. That was really cool. Really good to get it's really good to get the opportunity to speak to someone at that level in their career, so you can get an idea of what, you know, what it's really like, if it's for you, if this is something you're going to enjoy going forward, because yeah, rare opportunities in academia to see what it's like on the outside. I seem to remember, you know, you're around academics and all they've ever done is be an academic. So, you know, the reality is most people who go through university and do graduate school, even like if they go and do a PhD, most of them don't end up being academics. So it's kind of nice to see, you know, what the other side is, because it's actually most of them. Yeah, and it's good. Like, yeah, what do I want to say there? It's like, I think it's a good career path. Like, it's kind of preferable to academia in a way. For me anyway, for my personality. So yeah. I don't know if you maybe you get the other impression. Coding is a thing. There's lots of other opportunities. There's a broad range of types of careers you can have with mathematics once you're out. I might talk a little bit about that later on. Cool. So yeah, that's me for that. So we're up to Unit 2, just a refresher. So for you and for me, so I remember what we did. So last time we've done our bubble sort to death. We saw that it was quadratic. It's way slower than what's in base with standard sort. Started talking about data structures. These are super important. Again, the whole point of a data structure is the way you keep the data in memory is going to do most of the work for your problem. So for different problems, you would use different data structures. The idea is to pick the one that works for your problem. So that's the thing. So you've already seen plenty of data structures. You've seen arrays. So we talked about arrays, and we talked about these funny things called pointers, which point to where the data actually is in memory. So rather than, it's not what's in the memory, it's where is it in memory. So that's these funny hex addresses for where this data is laid out in memory. And you'll see one of the things, a detail of the implementation for arrays is they'll typically put them in order in memory. So resizing an array is an operation that will kill you, makes it really slow. So if you're trying to go fast, don't do that if you can, but you can't always know what you're going to do beforehand. So sometimes you just have to live with it. We talked about multi-dimensional arrays and gave a demonstration that, you know, they're just fake. They're not really 2D in memory. They're actually linear in memory, but we lay them out in a particular way. Different programming languages do it different ways. You can see in Julia, it's going down this way. All the ones, if you look at the pointers, they'll all be next to each other in this direction. And this has consequences for speed. So we did a simple thing where we're going to sum up the matrix by going over the rows first or over the columns first, and one's like 10 times faster than the other one for this pathological case. Normal array, not such a big deal. It's probably only going to be like 1.2 times, like 20%. But if you have a really strangely distributed data, like when Megan was coming in and talking to you, points is one. Like there really is a huge consequence for if you're going to lay them out as an array or as a matrix. You really don't want to do them. You want to do them this way, not that way, if that makes sense. Because you want the things that are together, the kind of, depending on the kind of operation you're going to do afterwards, you want that to be fast. Yeah, so we saw that. So 10 times faster for this one, but it's really sized quite disgustingly. It's 500 by 1 million. So really funny shape. So if you go through it the wrong way. Next one, super useful one. I said a little bit about types, gave you a first little introduction of structs in Julia. That's just not in the notes because Andy's going to do it again. Just this thing of like data modeling is difficult. You can't do everything with arrays and floats and ints. You kind of want these composite things sometimes. It's actually really hard to design those things up front. So a useful data structure is a dictionary where you can think of it as a key value store where you go, here's a bunch of stuff with keys that I know. If I want to access what's in them, I can get the value back out. Super useful. And big thing with keys is that the actual thing is you want this order one-ish access for keys. So that's super cool if you can get that. You can go like, if I want to see if a key is in the dictionary, that's going to be really, really, really fast. So that's the cool thing about dictionary data structure. Checking a key and a value is super fast. It's not really order one. Detail about hash collisions if you want to go further on and learn about the implementation details of dictionaries. If you go and look at hash tables, you can get this thing called a hash collision, which makes it all slow. So not really order one-ish. And this kind of thing that you can do that's kind of like an abuse of a dictionary is a dictionary with keys but no values, acts like a set. So you can just use your data structure for a dictionary, don't give it a value, just give it keys, then you've got a set straight away. So it has the same properties of a set. You only get, if you push the same thing in twice, you only get it once. Like repeated elements won't be kept, just the unique keys. And all these set operations will be fast, like checking if something's in a set is just the same thing as checking whether a dictionary's got a key. It's order one-ish, so it's really, really fast. Compare that to an array. If you've got an array and you want to check if a value is in the array, it's going to be really slow because you'll have to iterate through the array to find out where it is in the array. And generally, that's going to be slow. Little hint with arrays, though, is a trick you can do if you want to make the inclusion test faster. Let's see if I can do this. Julia, we've got in, talked about this. So you can do this for arrays and sets and dictionaries. You can check whether something's in a collection. So I can go 1 in, 1, 2, 2, can't say it, 2, 3. That returns true. If I do the same thing with a set, that's true, but the second one will be much, much faster. One thing you can do, though, is you can go, I think it's in sorted. You can do it for an array. If you know that the array is already sorted, let's check how we use this guy. So if you know your array has already been sorted, like you've sorted it before and you're just going to leave it sorted, testing whether something's inside a sorted array is going to be way, way faster than an unsorted array because you can do this kind of bisection thing to quickly get to where the value is going to be. So that's a little trick for you. But yeah, you can't use I tried to use it as infix and it doesn't work that way. You have to use it, you have to use it as a prefix function. So in sorted, 1, 1, 2, 3. It's true. That's the same, exactly the same thing as this. It's just the algorithm it uses to do it will be way, way faster. That's useful, but sets, you get all these things you'd want to do with sets like intersection, set diff union, all going to be nice and optimized. That's a quick thing you can do. Just showing this array access thing. So we're going to just check if a value is in an array and versus a value is in a set. And we can see that for the array, it's way, way slower than if it's in a set because of this thing. It's this order 1 versus order n type lookup thing, or order log n, I think it is going to be for an array. You can probably do something clever rather than having to go through every value. I'm not sure though. Okay, so then the next thing we talked about was a special data structure called a heap. So this, the natural way to motivate using a heap is this thing called a priority queue, where you go like, I've got a queue and I want to do the next most important thing in the queue. So the idea of a heap is it will really quickly tell you what the next biggest thing in the data structure is. So if you've got an array, It'll always tell you what's the next biggest thing, or you can flip that around and make it the next smallest thing. It's just a trivial change to the way the algorithm works. Not going to tell you too much about how the implementation of this is now, because I think you guys get to do it later, get to make your own heap, to do discrete event simulation with Andy. You'll make your own priority queue. Just this funny tree structure like they all are. The thing you want to do is you want to add. If you think about the desired things you want to do with this data structure is you want to quickly be able to add them with the priority, remove the thing with the highest priority. That's the number one thing you can do. That's the most important thing you can do. And you want to be able to modify an individual's priority. So they're the kind of three fundamental operations. So push, pop, and then just modify is what you tend to call those things. Did a naive implementation of this with an array, and it's really slow, but if you use a heap, it's really fast. And then you can abuse a heap to make a thing called heap sort. So again, bubble sort is n squared. That kind of sucks. How can we make it n log n, like the built-in sort seems to achieve? We can do it with a heap because it's got these fundamental operations you can go through and count them up, but basically it looks almost like no code because you're abusing the data structure. I'm not abusing it. You're using the data structure. It's kind of a strange way to use it, but basically you push it in, you make the heap as you push them into the data structure. That's this first bit. We start with an empty heap. We push our values of our array into this heap each time. And then when we read them out with pop, it'll read them out in sorted order. So it's easy. It comes out really, really, really quick. So if we do heap sort and we do a bit of timing, see it scales way better. And we do a little bit more careful timing, heap sort versus built-in sort. Seems like they're scaling the same way, but the coefficient out the front is worse. That's where we got to. Yeah, it seems kind of magical. I think, it's got to be careful that when you're looking at this, and we've got my heap sort. Oh, sorry, can't find it. Yeah, it's using this thing from data structures, binary min heap. And you push into it as if it was an array. So I'll just do it just again, using data structures. H equals binary min heap. Oh. So we've got H, it's got nothing in it. If we push H2, H is the thing with 2 in it. If we push 5, 1, they're coming in random order. And then if we pop H, we get 1. If we look at H, it's missing 1. So it's kind of destructive, this operation of popping. It edits the thing underneath you. Again, this is why you've got the exclamation mark as a hint that you're mutating the thing underneath you. If you pop H again, out comes 2. Pop H again, out comes 5. Pop H, nothing in there, you get an error. Is that clear? So this kind of thing, we're just using the data structure and these two fundamental operations of push. So when you push, you have to rebalance this, you have to reconstruct this tree, you have to edit the tree underneath, make it work for you. When you pop, you're reading off the next most priority thing. Cool. So it looks like almost no code. You're using a lot of stuff under the hood though with push, pop, and this heap data structure. Little bit of, does anyone notice this? I probably said this with types. Tend to use this capitalization for types where it's like capital B, capital M, capital H. That's a hint that the thing you're using is a type underneath. And again, like all these things, more or less documentation depending on how exposed this stuff is. I think this one's probably terrible documentation. I think we demonstrated that last time. Cool. That's using a data structure to do most of the work. That's a really common thing. So I was saying this one, Megan's talk last week, common thing with points, like we've got a LiDAR thing, we've got a point, we're going to go, give me the 1,000 closest points, like sort them by order. I want the 1,000 closest things and their distances to this point. You can't do that, so you have to use a data structure. That's and in that case, use something like an octree or a quad tree is the typical data structure if you want to go and look up how that's implemented. Okay, so quick sorts. I'm not actually going to talk too much about either of these two because I think it's kind of stuff you can do yourself, and it's a good process to go through this yourself because I think it's part of the homework. You've got to implement it yourself anyway, so you've got to understand it yourself. Here's just sketches of the kind of strategy you're using apart from quicksort. Apart from heap sort. Heap sort, we've used a clever data structure to do most of the work for us. In this case, we're going to try a different strategy where we're going to try this divide and conquer strategy where we're going to cut the problem up and recursively go down. And then you go, if you've got sorted sub-problems, you can just stick them together in a quick way, problem done. So probably going to talk more about merge sort and quicksort. I'm just going to wave my hands up because I think that's all we're going to do. If you've got questions about it, come and ask me or ask your tutors when you're going to go and try and implement this one. Go off and read it yourself. We've got links and resources. I think that's fine. So merge sort is a funny one. I'm pretty sure merge sort was von Neumann, the mathematician. It's like the first person to implement merge sort. So pretty famous in computer science, but also pretty famous in maths and physics as well. Kind of a super genius who did everything. But this was the idea. The idea is that we want to recursively solve a recursive problem where we're going to go make it into a bunch of subproblems and then just stick them all together at the end. That's the idea of merge sort. So it uses our old friend recursion that we talked about early on. So the function will call itself. And we'll just go through. This is a fairly poor implementation because it's doing a lot of array allocation, which you don't want to do if you want to make it really fast. And that's one of the motivations for quicksort. So like quicksort's cool because it's in place. Like you can just do it on the array itself and you've just got some pointers jumping around. Whereas merge sort, if you do it badly, like we've done it here, you'll see that it's bad because of how you'd implement this on a computer. As I said, arrays, you don't want to be allocating them because it's slow. If you can do it in place, and you can do merge sort in place, it just looks a lot uglier. So that's not what we're going to do here. We'll just go through this one at a time. So we'll make some data. Equals rand. Okay, we've got some random numbers. N equals length of data. So basically, because it's recursive, we're going to go all the way down to the smallest. What's the smallest sorting problem that makes sense? I guess there's a question. An empty list, yeah. And then one up from an empty list would be one element, right? And then what's the first non-trivial one? Would be the 2-element case, right? Well, we've got 2 values. It's an array with 2 things in it, and we want to put them in order, which is sort of the bottom problem of merge sort. So the idea is you want to recurse down until you've got like 2 things, and you just go put them in the right order, and take the sorted list, put them together because you know they're sorted, and you just got to work out, fix up the details in between. That's the whole idea of merge sort. So when you put them back together, this is sorted, so there's less work to do because you already know these are sorted arrays. So first bit is this thing, if you said, like, is it an empty thing? So we've got this short circuit evaluation where we're going to go n is length of data. If n equals 1, return, because you're down the bottom. It's just the thing. And we're going to decide a partition. So p equals n div 2. So that gives us 5. So this is integer division. So this guy / div. If you're not sure what it is, just ask for help. So the quotient from Euclidean integer division, generally equivalent to the mathematical operation without a fractional part. So you can call this with div xy, or you can do this operator to make that guy that's in the notes, type div / div tab, and you get div. Okay, so that's just to split this into 2. And then this is the recursive part. We're going to go my merge sort. We're going to use the array indexing. So this is kind of bad. I sort of said, don't use 1. If you can, use begin end. But anyway, haven't done that here. So what we're going to do is we're going to cut data from 1 to p, just to be clear. That's the first bit of data. So this is our full array. We're going to take the first 5 elements. Then we're going to take the second 5. We're going to go p plus 1 to n. I don't think I said what n was, so it's going to crash. Oh, no, it did. So it's just the second half. So that's going 0.83308 up to 87. Cool. And then it just calls my merge sort again. So the recursion happens almost straight away. So it's just going to go back in, my merge sort, n equals length of data. So for this little one, so we'll say L1 equals that. We're going to go n equals length of L1. It's 5 long now. We do this integer division thing again. So what's this going to do? Because we've got this case now that it doesn't divide too evenly. So, oh, well, you're out of luck. You've got to get 2 and 3. So first bit's going to be 2 and the next bit's going to be 3 to 5 for this one. So again, you recurse, merge sort until you hit this condition where it's going to go, right, cool, nothing to do. And then this is the fussy bit where we're going to keep running indexes from the top and the bottom. I don't know why that says hash will. That's kind of strange. Anyway, so loop on indexes of destination array. So we've made data new, which is a vector L type of data, undef length of data. Okay. So again, that's kind of a yucky way of initializing an array that's 10 with undefined. You can do that lots of different ways. You could initialize them as zeros. Undef is probably the best thing to do because you don't really know what they're going to be yet. So you're initializing an array, you know how big it's going to be, but you don't know what's going to go in there. That's what this, oh, that just fell. That's what this vector L type of data. So that's the type elemental. I went through this one last time. So L type of data. If you're unsure what bits are doing, it's saying, oh, it's float 64. So I'm going to make a vector of type float 64. If I didn't know how big it was going to be, I could just do that. If I do know how long it's going to be, I can use this tuple. I'm going to say it's of type undef and length of data, blah, blah, blah. So it's 10 long with stuff you don't know what it's going to be in there. That's the whole point of that bit. So this is the fussy bit, and this is the bit, I think it's kind of like, I can say it, but you have to go through it yourself to get it, because it's like, this is one of these things where you kind of, with my brain anyway, I have to go, I can't really understand something unless I can implement it myself. And me talking to you won't help you with this. This is the same idea with quicksort. You kind of have to go through it line by line and just check through. I can do a little bit of it in this lecture, but I'm kind of conscious of time. So, and I think it's better if you do it yourself. But we'll go through this bit. You're going to keep running indexes and we remerge the sorted arrays. So you're going to go, so think about this recursive structure. Think about what the calls are going to do. You're going to go all the way to the bottom and you keep, the idea is though, is that you just, with some trickery about indexes, you're going to remerge these things as they bubble back up together, as you put them back together. So you got to keep track of, you got to check it, just keeping track of when things are going to sort. So if top data is finished, so what do I want to say? So yeah, so all the comparison stuff, like this is just keeping track of pointers and accessing data. So that's kind of boring, but the real comparison bit's just this bit, where you're actually putting something into the new array, data bottom, blah, 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 else data top. So that's the sort comparison bit. It's just that bit there. That's all it is. And you're just fussing around with indices apart from that. I think that's kind of bad explanation, but again, I'm going to say it, you've got to go through it yourself. Yeah? The top is log n. Yeah. So we'll go through that in a little bit. It's kind of like, all those bits are fast because you're just sort of going through the array. It's just like order n, basically, to do all this fussy bit. Like when we go through analysis of the runtime, that's the kind of bit you can say, because you just go through this bit. For I equals 1 to n, you do a bunch of comparisons, set some data into a new element. What's going on basically, like we have two sort of arrays and you put them back together and you got to work out, interleave them back in. Right. Yeah. So just going along each of the two sorted ones, whichever is like bigger, yeah, because you don't have to resort the array, you just got to kind of interleave them back into one another. It's like I look at the pictures and I go, oh yeah, that's what it's doing. Pretty much every time. Okay, cool. So that's merge sort. It's kind of a bad implementation because of basically that step. reallocating's bad. Like that's going to be the thing. So this isn't going to be a super efficient implementation. I'd say just pull it apart, go through it, each recursive bit, do it yourself on the REPL. And in terms of timing, this one's not great. I think I'll just run it just because I can. Yeah, my advice would be lots of print statements, just so you can see what it's doing everywhere through. So we'll just check this timing. So Rancid, this is sorting a million things, so way better than bubble sort still though. Oh, sorry. So 10 to the 6 random integers. So we can show, this is just testing the results. So if we want to do, we're going to run merge sort on data and sort on data. These ones aren't in place, so they're not editing data underneath, so we don't have to worry about reallocating. You notice that we're using not the sort with the exclamation mark, so it's not going to change data underneath our feet. So we can just sort these two, get these two output arrays, and we can check whether they're exactly the same. So that's true. So just to be clear, if I run that on that, and I run sort on that, they're both fast. And we're just, the equality is just checking these two arrays that I get out, are they exactly the same? Probably not, yeah, that's what we're going to do. So that's cool, we get exactly the same answer. Useful thing when you're writing code, if you want to do this as a test, you can do this macro at assert. That's cool. Assert, what that will do is we'll give you a type of error that's useful. If you go false equals true, you're going to get this assertion error. It tells you what it is. This is a usual thing in programming, like when you want to, you want it to go kaboom in a way that's going to explain what you did wrong. That's the thing you can do. Cool, you get an assertion error. So the thing is, though, we want to check at time my merge sort data. Okay, all right. So for a million things, it's like 0.3 of a second, but again, inbuilt sort's going to flog it. That's just what it is. And the main thing is, so this is a useful thing when you're doing a bit of performance profiling, to look at this allocations, because this is saying like, how many times was memory allocated when I ran this function? So Julia gives you a hint about something dumb you're doing if you want to go fast. So general rule, as I said, allocations of memory, particularly for arrays, is not the best thing, because you've got to find a bit of memory where there's a chunk where you can stick them all together and there's a missing bit. It's actually allocated 500 megabytes, which used to be a lot. Maybe it's not a lot now, but you'd notice that. And this thing about garbage collection time. So haven't talked too much about programming languages and different styles, but I'd say we're all in high-level languages. Nobody's doing assembly. Assembly is the real low-level language. We're not doing things like LLVM. If you compare a language, though, like C or C++ with something like Julia, the difference would be about memory management. And in Julia, once we've made an array and we don't use it again, we kind of don't have to worry about it. It's not like it's going to hang around forever and eat all our memory. If we don't use it for long enough, this thing called a garbage collector comes along and fixes up behind you. It'll go, that's the thing, I'm going to get rid of that. So if, though, garbage collection is slow, because you kind of have to stop the program and go like, yeah, cool, I'm going to eat this memory, get it back for you. Garbage collection time is not a good thing. So if you're doing performance profiling in any of your code and you're seeing garbage collection times high, it's a sign you're allocating stuff when maybe, if you can think about how do I change this around so it's not allocating, it will go a lot faster. Just something for you to see. So you see, though, compared to inbuilt sort, 5 allocations versus 3 million allocations. That's quite a difference, right? So that's not great. And that's all we can see. Again, pull this thing apart, go and check through yourself that you understand what it's doing. It's very useful. Again, get that picture in your head of like, okay, merge sort, if I watch what it's doing, I can see what it's doing and get the picture. And this is like a cheat, really, for analysis of algorithms. we've got three parts. So we've got the sorting the bottom sublist, sorting the top sublist, and then merging the data. So merging is all this fussy stuff. That's all that stuff there. What we can do is we can see that this is a recursive problem. So if Tn is the time for sorting the data of size n, and then Tn on 2 is the time for sorting each sublist, right? That's just a definitional thing. You can see that time to merge two sublists of the order n. So that was your question before. So like, what is if you go through the fussy bit, what's the order? It's linear in the size of the elements. So that's order n. You got to run on the whole length of the data set. So we've got this recurrence relation between, like, if we had a full list and we got a list half the size, there's a recursive definition for like what the runtime would be. And somebody nicely did a proof for a very general case of this thing, which means we don't have to worry about it. So we can just go, this is a special case of this more general thing. So these types of recurrence relations, they kind of covered everything that's of this form. You can kind of just plug it in and go like, oh, it's going to be n log n, or it's going to be n squared, or it's going to be blah. So this guy is called the master theorem, which is kind of a special name, I'd say. It's kind of arrogant. It's like, yep, that's fine. It's surprisingly recent. Like, this is 1980. So like, it's not an ancient thing. It's like not quite my lifetime, but you know, just before I was born. If you have recursive problems of this type, so anything of this form where you've got like, you know, what's the order of the bit on the sub problem and then the fussy bit? If you stick all those guys together, so time to create the sub problem and combine their results, that's the Fn bit. So if we've got a problem of this form where it's like, we know A, B, and Fn, basically we can just plug it in and they did all the cases and you go, oh yeah, just plug that in, blah. So easy. You just have to understand for your problem, if you want to apply the master theorem, like which case do I have? So you just have to basically build this recurrence relation. And so yeah, turn the crank, turns out it's n log n. Too easy in that case. I'm not going to go through a proof of the master theorem. It's beyond this course. We don't care. We just want to know the results and we can empirically verify it and go, yeah, that seems reasonable. Cool. I think that's just waving my hands at it again. This is all homework stuff. So, you know, if you want to show quicksort or something like that, you can apply this sort of logic. Because again, quicksort, where am I at? 5:30. It's cool. Yeah, quicksort's another divide and conquer algorithm. So it's part of homework 1, not going to provide an implementation. There's pseudocode. You can go and do it, come and ask questions. Putting it all on you guys, exercise for the reader. Big thing with this one is like you don't really need to reallocate these data structures. Like you can just keep some points and a pivot and move around and you turn it into sub-problems that way. So it uses array indexing in a kind of clever way to just work on the original array, or you can do a copy on a copy of an array. You just keep a high index, a low index, and work out a partition and pivot, and basically do some swaps on that. So again, just wave my hands at this. Again, it's another recursive problem. That's all I'm going to say. I think you can go and have a look at it yourself. The interesting thing with quicksort, and this will bite you when you implement it, is this nearly happens every year someone does this. It's like they've done their own quicksort and they go like, oh, it's running slower than bubble sort. And the interesting thing with quicksort is that the worst case complexity for quicksort is n squared. Whereas if you've got something like merge sort, I think we had our sorting zoo back up here. I'll see if I can quickly find. It's way back up. Here we go. So interesting thing with sorting is we look down at this list. We've got best case, average case, worst case. So we've also got memory. This is a really important one. Like practically, like when computer scientists are doing it, they don't care. They just kind of, most people care about the computational complexity. It's all these three guys. Practically, I care kind of a lot about this one. And this depends on the implementation as well. Like we can do a really terrible implementation of merge sort like we did in the notes, and this will be even worse than order n. And that can completely kill you. But merge sort, on the other hand, best, average, and worst case is all n log n. Quicksort, however, worst case is n squared. And it depends on this pivoting strategy and the partitioning strategy you do decides which is the worst case. And I think the one we've given you in the notes, the worst case happens when it's already sorted. So if you're running quicksort and you go like, this is terrible, why is it so terrible? Because the partitioning scheme you've used and it's on an or, it means that on an already sorted array, you get this n squared runtime, which is kind of funny. I think another hint going back in time, we said, oh, you can go look at base sort. And I think I saw this guy. So this one always stands out to me. There's a function they've defined that is sorted. So if you're going to run quicksort, you really want to run is sorted on it first, because you don't want to hit this, depending on your partition scheme, like you really don't want to hit this n squared complexity. If you've chosen a particular partition scheme that your worst case happens straight away. That's just a hint. Sorting. Yeah, so again, quicksort, n log n in best case, average case n log n, worst case n squared, merge sort, blah, blah, blah. Bubble sort will be down here somewhere. Bubble sort order n, that's the best case. That was that thing. It's already sorted. You can just go through and go, hey, just got to check all the things are in line. If they're all in line, I can stop. But n squared on the average case and worst case. I'll point this one out because this one, I'm pretty sure this is the default in Python now, this tin sort guy. And this has a best case best case complexity order n, average and worst case n log n, and memory n. So there's these hybrid algorithms. They're kind of like halfway between merge sort and quicksort. And yep, still not a solved problem, but which is the best sort? Kind of depends. They all have trade-offs. For me, as a practicing software developer, it's this memory one that's usually a killer. Like you can't negotiate with memory. Like you either have it or you don't. If you run out of memory, the process gets smacked down. So it's kind of dead. I like these cool pictures. Hopefully I didn't play the sound for this guy, but if you want to visualize it, this is quicksort, how it works. I think I showed this one. You can sort of see this recursive thing. People have animated these things. So you get this idea of what quicksort's doing itself. And then recurse down. Then go back up, recurse. Again, this is the kind of thing I'd encourage you to do with a small problem in the REPL and just do lots of printing to just see what it does. And this is merge sort, where it's going to go like recurse down, end up with merge sublists as you bring them back up, and you go, ah, cool, that's merged. So do the sub problems, merge them back up, do that fussy bit where you're going to join them back together. You can kind of see what it's doing. I'd encourage you to do this a bit line by line. Then done. You can go and watch 6 minutes of sorting if that's your thing. That's heap sort. I don't know what the colors mean. Yeah, and then you just, yeah, so that's the array, the heap construction, and then you just read off in order. So cool. I think they're great. Yo.
Yeah, Wikipedia page for the interface merge sort, it didn't have anything listed for the best case.
Okay.
Do you know why?
I'm not sure why. I'm not sure. Yeah, no, interesting. I don't know much about. Yeah, that's interesting. I assume they're the same as above.
Yeah. Oh, possibly.
Yeah, it's worst case complexity is n log squared n, which is kind of interesting, but you'd take it for that. Like, that's cool. I'd just go, yeah, there's a zoo. I'm not a specialist in sorting, so I'd go off and actually look at an implementation or try and do it yourself, and you'll understand it better than me. It's like, cool. All right, sorting. I'm kind of done with. I'm sick of it. I'm sure you guys are too. Anyway, so yeah, again, got to go off and do it yourself. Look at lots of these visualizations, go through it line by line and pull it apart so you understand what this recursive structure is doing. I find those animations super useful for thinking about what it's doing. they're very clever. Like, I won't pretend that I could have come up with quicksort or merge sort. Like, I think they're actually really, really clever. So, you know, it's kind of like, I'd be pretty happy if in my career I'd come up with something that cool. But, you know, so don't expect these things to be easy to understand. You kind of got to work through them. That's just the way it is. Yeah, I guess interesting is asymptotics. Like, you know, you can't, there's a proof about what the best case complexity is, well, best average case complexity is, and it's n log n. So they're all kind of the same, bar details about implementation apart from that. So you can't really win beyond n log n. Different problems though, nobody knows what the best case is. Like I said, matrix multiplication. It's like, what is the lower bound for matrix multiplication's complexity? Nobody knows. There's no proof for that. So you're all young and smart. So one of you can go off and prove what that is. I hope it's n squared. I'd be really surprised if it was, but if it was n squared, I'd be super chuffed. Okay, cool. So I jumped ahead last time and talked to you a bit about Git. Has anyone been traumatized by Git now? Has anyone had merge problems yet? Yep, cool. Do you want to talk about them like therapy?
It just told me what to do.
It told you what to do? Yeah, I'll talk a bit more about that. We'll sneak up on it by just talking about how Git works based on crusty old Unix tools. Big part of being a software developer is using tools though. Like, so it's kind of weird coming and teaching a course. It's like, I don't really work alone ever. I never have to do a problem on my own. If I do, it's like kind of like my manager's messed up. It does happen a lot, but you know, like, you're trying, you know, you always work together. So it's cool, you know, we do these problems, you do the homework together, that's cool. You spend a lot of time with tools, and it's like, kind of like, if you can use other people's stuff, you just use it. So we'll talk about that. And it's kind of interesting because we're going to get you to implement everything, and there's things about plagiarism and cheating, and talk about software licensing. But, you know, basically the thing I want to communicate is like, this is an academic environment. When you're out in the real world doing real things, use the things you're allowed to use. Be productive. Like, academia is a bit weird in that way. This is like, they want to teach you, and teaching you, they kind of have to force you to do stuff. But a lot of things like sorting, if there's a good implementation, it's important that I understand how it works, but I just use the one that someone smarter than me made, because it's going to be way faster than anything I did myself. That's kind of where it's at. So using tools, and one of the big tools is like the actual, we're going to talk about Unix as a tool as well. So like, we're going to, I guess most of you are on Windows, that's kind of clear, but we give you a Unix-like environment by Git Bash because it's really productive. And it's kind of, depending on the type of developer, if you go into software and depending on the type of developer you end up being, I use Linux all the time. Like, all servers basically run Linux these days. So it's important to learn a little bit about that. We talked about Git. If there's any particularly pointed questions about use of Git, we can take that. And just talking about IDEs. So that's where we're going to go next. I'll start with Unix. So, oh, didn't do what I wanted when I clicked that. Close some of these guys. Okay. So, this idea of an operating system and what it's doing. Down underneath, it's some grotesque level of just really fast logic at gigahertz. There's this little Turing machine on the CPU that's doing all the real work. If I wanted to talk to that directly, I'd be writing assembly. If some of you go on, has anyone mucked around with microcontrollers? Has anyone got an Arduino? Yep, so like you can not have an operating system. There's this whole class of computers that run your toothbrush and, you know, any little gizmo that you've got. They don't actually sometimes have a full operating system on these days, but usually, historically, it'd just be a little microcontroller. You don't get a full OS, you just write C code on it and you can muck around and do it. But that stuff's kind of gross. Like, writing an assembly sucks. Writing in the layer up from that in C kind of sucks. So it's kind of fun, depending on your outlook. But you can't be as productive. Like, you can't write I can't write big complicated programs in C. It's kind of a monster. But if you're trying to go fast, you know, that's kind of what you have to do. We kind of want to be up in this pile of abstractions where we're just talking at it in something like real language and we can get it to do what we want. That's kind of what the computer's for. To achieve this, we have this thing called an operating system that manages all the software and the hardware of the computer. So it's kind of this gross thing of like, you've got a file system, you've got memory, you've got running programs. You can run multiple programs at once, which is kind of crazy if you think about it. You've only got, you know, a couple of computers on your computer, a couple of actual physical things, and they're going to swap in and out of how many things. I can have Chrome running with 800 tabs and kind of is pretending like I'm running, you know, thousands of programs at once. Is a thing, fairly normal thing, or hundreds. How do you actually deal with that? Dealing with I/O, so like I'm moving my mouse around and I press the buttons and it's going to show stuff on the screen. Dealing with networking is a bigger and bigger thing these days. Is like, you can typically, if you want to scale to really big problems, you have to deal with that. Yeah, so yeah, you've got the shell. So there's the operating system underneath and there's a shell, and they call it a kernel. So the Linux kernel, Unix kernel is like the bit in the middle, and then you've got the shell around the outside where you're poking things down to it to get it to do what you want. People had to build this stuff. Unix was the grandfather on mainframes. The idea back then was they wanted a portable operating system. So usually they'd compile it on the computer to have an operating system on that computer. And they tended to write their own back then, crazily. So like they were big projects, you know, multi-million-dollar projects. So there'd be an operating system for that big computer running in that big university or research department. They wanted a portable one based on C, and that was Unix. I think I got the plot. If you want to see the history of these guys. So back in 1969, there was this unnamed thing. They didn't even give it a name because like people didn't think about software the same back then. They just shared it with each other and they didn't care. Like nobody was trying to make lots and lots of money off of it. They didn't realize maybe. I think they could see the future, but nobody else could. So they kind of just were very free back then. It's kind of funny that this was a thing that people just, you know, they just gave it to each other when they worked at a university. They just give it to the university and they passed it around. Had these initial versions of Unix, and then that turned into, it already split back in the 70s into these things that ended up turning into Solaris and HP, running their server stuff. BSD itself still exists now. That's an operating system, FreeBSD, that you can still get. And funnily enough, macOS is based on the same historical path. So it's Unix-like, and it's commercial, but it started off with something free. So go figure out what that means when we go to talk about licensing. I don't know exactly the history. There's these funny things called Minix and Linux. I think this started, it started in the 90s, early 90s by Linus Torvalds. That's the one I tend to use. There's a whole similar plot like this for all the different flavors of Linux that exist in the wild now because it's an open source project. Yeah, but like I said, we'll talk about it in licenses, but if you've got an Android phone, underneath that, it's Linux. If you've got any server for any web page you go to, the thing in the background is going to be running Linux. These days, it's kind of taken over. It's super useful to know about. So bar all that stuff, you know, but the most popular operating system for PCs is probably Windows. It's not Unix-based. It's another thing. But a big part of this is learning about the shell. So you've seen me open a terminal here. This is a thing called bash, which is born-again shell. This is a shell. So this is a thing you use. Bash itself is a programming language itself, but we'll talk a little bit about that. But basically, you've got some navigation stuff. Again, we don't expect you to build up command line stuff, but you know, you should if you can, if you want to go, especially if you want to go forwards with this stuff, because you need to learn it. Basically, we've got some little things here. So little bit of cheat sheet for stuff you want to do. I'll just demo. So here's my stuff. LS is like the first thing you're going to do. That's for list. So it will tell you if you're in a folder, what's there. If I want to change directory, say I want to go down one directory, and hopefully that blue is not too hard to see, but if I want to go back down, I can do ... ls, something there, I can go down, cd ... If I want to go back up, I can go whole silly test repo, ls, back in here, cd source, back up. Okay, and if you get lost and you want to know where you are, pwd is your friend. It will say print working directory. What do I want to do here? So another bunch of basic commands is I've got this. What do I want to do? I can delete things. I don't really want to delete anything here. Okay. I'll make something to delete it. So what do I want to do? I think I'll take a break and I'll start back up again with this stuff because we've gone to 50 minutes. Take a 10-minute break. Come back. I'll do a little bit of a demo of this stuff. It's just some basic commands so you can see how you work in a Unix-like environment. Okay.
Should be. I've done it all AD with my bubble sort and quick sort and everything. And I was just timing them. And no matter what I do, my bubble sort is twice as fast as the inbuilt sort. And it is sorting it because I checked.
It looks like it's doing nothing. It's like zero allocations, which is kind of.
So this is the bubble sort.
Yep.
It works with the names and it does sort it because when I checked it down here,
So
I can comment out this and show
the only thing I'd be checking for is checking your reads before you do the type.
yeah,
So it might already be sorted.
yeah, so that should show here once you know it. I did only give one. Yeah. So it gives that the sort is not equal to the original data, but then it says that the bubble sort is equal to the sorted. So I don't.
Put a bit of debugging in your function just to check because it would be surprised. I'd put in like that conditional you've got to break out.
Yeah.
Like if not is swapped. So if not swap, right? Check if that's getting hit. That would be my advice because it might just be walking on the first one.
Because it returns that it's the same, like the sorted ends up being the same as the inbuilt sort.
So it's not in place. So your bubble sort is not in place.
Yes.
Okay.
So yeah, but and then when I run it with 10 to the 7, it ends up being 3 times as fast as the inbuilt.
I can't see it. It's surprising if true.
Yeah. Yeah, so that the quick sort is slower than the inbuilt, which is good.
Yeah.
Yeah, that's the quick sort.
I can't see. So right. That's fine. It's basically the same as what's in the notes, right? No, something surprising. You just got your swapped.
Yeah.
Yeah, I'm putting a little bit of different statements in there just to check. Otherwise, publish it. Yeah, you want to go publish it.
If you had any particular tips for the goal back question,
Okay.
because I'm hitting a bit of a limit where it's like, so that was for 10 to the 4. I think 10 to the 6, it's taking around 15-20 minutes to run.
Okay.
So I've pulled out the sieve to make sure it's out of function. And I've done a few little optimization things, but it still seems to be going for quite an excessive amount of time.
Yep. So I guess my biggest thing would be, do you understand what's bad about the original implementation?
Yeah, they had the sieve inside the function.
So it's
doing
calling it
every
every
single
time.
So
Okay.
yeah, I've brought it out, and then I have a little thing here that basically finds the maximum index you want for each end, and then it just takes like the longest prime that you need for the question, and then for each end it just goes up to that index.
Okay, so primes is an array.
Yeah,
So be careful though, because you haven't given that as an input to this function.
yeah,
So that's the stuff about type instability can be a problem. So that's one thing that might be going wrong.
yeah.
You've done intersect and okay. Gotta make sure I understand how that works. That's cool. Okay. So again, if this is an array, I'm guessing.
Yeah.
So that stuff I was just saying in the notes about intersecting that being fast, that would be much faster if it's a set.
Actually, it's not. I
It's
tried
not?
that, and it's slower if I do. If I like run it for that, it'll be yeah, having a few bounds error issues, but that's sort of later. It's like 0.57 around that. If I do it as if I actually no, if I do it as a set network, right? Because I can't have a minimum.
Oh,
index.
okay.
But it was like would have been around 0.6 or something, so it was running slightly slower if I use sets.
Okay.
Yeah, so no, that is something I did try.
Yep. Okay. Just like my advice for this stuff is like wrap it all in functions. So
Yeah.
you're not getting this global problem where it's has to promote to type.
Oh, okay.
That's like definitely what happened with this guy with primes. Because primes is really an input to this. Like
Yeah.
if you wanted to run it for a bigger set of primes than what you pre-calculated, that sort of stuff.
Yeah, okay, I'll try adding more functions to it.
Yep.
Yeah, cool.
No worries.
Thank you.
Hello.
Interpret what this question is asking.
Okay. So, in general, this passing is only a necessary condition for fishing. Like some sort of bargain which can exist that slips through the test. So is it a real test, I guess? Like can you think of a pathological case that would break it?
Yeah, I got it. The only one that I've been successful with so far is the other way around, where the test says that it's false, but it's not.
Yeah, that's fine.
Oh, is that?
That's fine as well.
Because it says it. I know, like I know how to like slip through the test to me. It feels like.
Yeah.
I got false negative.
Yeah, okay. I can't remember. So what's the test?
My thing was just exploiting this one. It's like I made the A term and the negative term.
Okay.
Yeah, it works, then it's good. It's nuts. But it's
I guess what happens if it's like a pseudo quadratic would be the other one I'm thinking. What happens if it's like linear? So pretending to be quadratic and A is 0.
Yeah. Actually, yes, remind me of the second half of that question.
Yep.
So it says for the real roots of quadratic function, do we use the original function or the one after we made the changes as
I'm not sure. That would be one I'd stick. Just to check what he means exactly.
Yeah, because one of those things is actually just got
Yeah. So think about like no real roots, so purely imaginary roots, it's linear, that sort of stuff.
Yeah.
Single root, rather than two.
Yeah.
They're the kinds of things I would be thinking.
Yes.
Yeah.
And then just like I'm going to start off that with the
Yep.
So we have like numbers here. Let's say that these are
Yep.
numbers. Is that like it still has to guess, or it has to try and like make it decide.
It's fine. Like that stuff tends to be fast.
Okay,
So yeah, it's not too bad. So that's a super type. So like this is all stuff Andy was talking about too. You have to have an abstract type, just like next in 3 lectures basically you get all this stuff, but like you can have a super type that has no methods associated with it, like or no implementation. Like it's just for like dealing with all the cases below this time. We usually find a fast one for that. A number is like the types like int, complex, all those different types. So That's fine.
So it just has to make that decision over like a smaller, I
Yeah.
guess, sheet, several steps.
Yeah, that's right. Yeah.
There is a
Thanks.
So I put in that thing there, the print,
Yeah.
and it does get it, and it's what's the thing. Yeah. So it gets to this once it's all finished. So it goes through, so it's all sorted, and then it gets to that, because nothing gets swapped, which it did.
Yeah. I mean, if you just run the timer, you have time on that. So you just ran.
Oh, yeah.
Yeah, that's the real puzzle.
It should be about 47 percent.
Doesn't.
Oh, that's right. Oh,
Yeah, you probably don't want to press that at the time. Anyway, so confusing. Hello. Oh, to do it.
So this is in context of the quick sort.
Quick sort. So if you're splitting, did you say so?
Flattening, so as in unnesting arrays. Splices.
Do you have an example?
So flattening with quick sort was have an array of numbers.
Yeah.
Flattening was bigger than less than pivot.
Yeah.
Splicing was bigger than pivot. Splicing. Yeah. Join them back in.
It depends. It's like usually not great because of array allocation stuff.
Yeah.
But it might be clever enough to work out that you're not really doing that. So the whole idea with
I guess the other way was to go index by index.
Yes. Yeah, that's the usual way you do it. Yeah. It's
And,
usually not great to do that, but sometimes it'll be tricky and just to find a middle radius.
Yeah.
And be clever. But it's not usually the idiomatic way to do joins.
and flattening, so unnesting arrays.
Yep.
How intensive is
Again, it's an array allocation, so
or unallocation?
or you're taking lots of little ones and then putting them into a new array that's like bigger. So it's like push, right? Like it's clever in how it allocates the new memory to do it. So it's like faster than it would be if you did it the dumbest way possible, which would be like every time you get a new element, you resize the array.
Yeah.
It does like a logarithmic resizing thing.
Is it better to splice and then reform, or is it better to filter and reassign it? Again, with the difference.
Depends on the problem. Like it really depends. So I'd have to see the code to be able to work out an answer. But yeah, if you don't have to, if you can get away with not doing that, that's the idea.
Okay, we'll get back into it. Yeah, just check I haven't ignored the chat horrifically. Okay, cool. Okay, so Unix, shell, bit of command line knowledge. This isn't super important, but it'll help you. So you may as well, if you earlier you see it, better you'll go. So I think one of your questions is basically doing this stuff. It's all pretty easy. We're not going to get you to do anything too disgusting. Yeah, so funny thing about all this stuff is that all of these guys are functions underneath. So much like in Julia, when I said, oh, if you don't know what it is, you know, do the question mark. In this guy, it'll be minus help. So if you're confused about what ls can do and you want to know all the options, so ls, you know, I just said, oh, it just lists the directory. It's like, it's way more complicated than that. It's much more complicated than that. And it can do a whole bunch of stuff with optional arguments. You can ignore stuff. Yep, a whole bunch of stuff I've never in my whole life used, but it's a complicated, and it's a little program. It's a little C program that's really well optimized, and probably it'll be open source, so you can go and look at the implementation if that's what you're interested in. That's ls. So so you're doing this command line stuff, you know, maybe RM will do it too. RM's the same. So like if you want to remove and you don't really understand what you're going to do, cool, you can remove. So Next one, like you want to remove a directory or make a directory. These are common things. So cd source, let's go in here. If I go make the test, go ls. Now we can see that there's a blue one. This is really bad on my screen, so I hope it's not too bad for you guys. There's a little thing, sorry about the colors, I'll make it better. I've made a directory called test, and if I want to rm test, it goes, I can't remove test, it's a directory, -r, now it's gone. You can move stuff around, so if I go back again, make the test, and I want to do something, let's take, so this is a useful one that's somewhat, we've got echo. Now this one I find funny because I said, like, you know, if you want to help, you know, you can do minus help. Echo is an exception because if I go echo minus help, it just goes help. I find that funny. I don't know, it's kind of like your best friend if you do something naughty. Just look at each other and go help. It doesn't know what to do either. If you want help for that one, you go man, I think it is. Gives you the full options for what you do with echo. So basically though, so that's just help for Unix stuff if you're doing it either minus help or man for manual. Terrible names for all these Linux things, all these Unix commands. If I go test, okay, it echo just basically echoes what it does. I can pipe this into a file, abc.txt, anc, who knows what that is. Okay, ls, there's this thing called abc.txt. I showed you this when I was showing Git. There's a whole bunch of text editors you might use. Vim is one. We can see abc.txt, says test. So that thing echoed, I just pushed it into this file. Escape, quit. I do have the test folder. And if I want to move abc.txt into test, I can do that. Now look, abc is gone, and then if I go into test, ls, abc in there, I don't want it anymore because I'm fickle like that. cd ... I've still got this test directory around, I want to get rid of that. rm -r for recursive, test, cool. That's basically all these little file handling, moving stuff around. This is all super useful. This one is in Julia. Has anyone discovered the magic of Control-R? Has anyone seen that in the REPL? Control-R is useful in Unix too. I'm actually doing this a lot, and I'm not telling you that I'm doing it, but when I'm in Julia, if I want to go back through my history, if I press Control-R, it will do reverse search. And I go like, my merge sort. Oh, I can go, and I can keep pressing Control-R and go back through the history and go like, oh, I did all this stuff here. My, and I can do, say I want bubble sort. There's my binary file. Went back too far. So I can go back through all the stuff I did in my history and go like, cool, there's that thing. That's all from Unix stuff too. So if I go Control-R, I can look through. Cool. That's super useful to know. And another one for the Julia one though, similarly, I do this one all the time as well. If I go func and I go like, I was typing function yesterday. If I press up, it'll bring back. I can go, up. It'll go through all the times I've done function in my history. So keeping this bash history or history of your Julia commands is super useful. And I'm actually crippled without it. I have no working memory anymore. I'm too old. And so like if my bash history goes or my Julia session goes, I'm like lost. So these are so useful to have there to go back through all the stuff you were doing. So I'll just point that out. Okay. So another bunch of stuff. So if you don't want to, if you can't be bothered, you know, going into a text editor, you don't want that much. What you can do is you can cat, which will just print out the things in a text file. I'll go that one just to see what's in there. I go cat. Goes, cool. It'll print it out in standard out in the bash thing. It'll go, oh, that's what's in that file. So again, if I go, say, into VS Code, same thing. Oh, okay, that's the test dot. That's what's in that thing. So if I can't be bothered using a code editor though, I can just do it in that guy with cat. If it's a really big text file, I guess it's like, say, one of these source code ones, and I just want to like poke around in there and see like what's in the top of this thing. I can do this thing called head. Say fun with linear algebra. That looks fun. It will give me the top 10 lines of that text file just so I can look at it and go, oh yeah, that's what's in that thing. Similarly, I can go, okay, tail will give me the bottom 10 lines. Cool. And that's useful when you're poking around in files and you go like, oh, what is that thing? I just want to see what's in there. Diff is probably the one I wanted to do. So I think I wrote, hopefully I prepared. Okay, intro. Okay, I've got this text file here. It was a dark and stormy night. And it was a dark and stormy night, and then some nonsense after that. Really useful thing you want to do is go through a text file line by line and see what's different about them. So that's this tool diff. So I can go diff, again, if you want help, minus help. Oh no, gotta learn to type. Basically, it will give you what you want to do. So diff, option, files, compare files line by line. So if I want to diff this guy, intro text, intro 1, was it intro 2 text. So cool. Gives me this kind of bit of cryptic Sudoku stuff where it goes 7, C, 7, 8. This thing's different. And it's different to night because it looks like I've got a typo. And I've also got this new line on line 8, which is just gibberish, which we can see when we look at these two things. So we've got intro and intro 2. It's really useful for code. And this is diff is what git diff is doing. So when you're getting merge conflicts, it's diffing these two files. It's running basically the same thing as this diff, line by line, and going through and checking line by line for what's changed, like what's new, what's coming in that's different. So when someone had a merge conflict, who had a good experience with a merge conflict? Nobody? Usually it's not so bad if the diff is simple. So the one you're going to get a horror show with is stuff like an IPython notebook where it's a big blob of JSON. And doing this line by line diffing will confuse the crap out of it, and it won't know what's new and what's come in because of the structure of JSON. Talk about that a little bit later. If it's just a Julia file, it's fine. It's simple stuff. Because it's just like any sort of normal code, diff will work really well. If it's some other data structure, diff will have a really big problem. That's what I was saying early on when I introduced Git. Don't put binary data into Git because it will get really confused. And the thing it gets confused by is it's going to go, I'm going to diff these as if they were a text file. This binary for data is not a text file. If I interpret it as a text file, it's going to get super confused and it's going to go, hey, these are completely different, even though, say, it's an image and 1 pixel's changed. It's going to go, okay, I'll do diff the whole thing and put the whole thing in there. It's not going to be happy. That's, I would say, yeah. So again, you're lots of young, smart people. If you want to go and make the next cool version control thing, make diff, semantic diff, much more powerful. So it goes, oh, this is an image. I know what the difference is for images. It's not if I'm pretending it's a text file. It's like, oh, I'm going to interpret these as pixels and go like that pixel's different to that pixel. Or this is a Julia program, or this is an actual text file, or this is Markdown, or this is JSON. I think the next cool version control thing will be much more powerful at diffing, and that will be the difference. So it can tell, what's going wrong. And I think like 80% of people's problems with Git is Git diff and Git merge problems, and it's just that it's not clever enough to work out what actually changed. So again, advice for you guys with the way you're working with Git, just keep in different files, don't tread on each other's toes. You won't have these problems. That's an easy way to work around it for now. Cool. So that's diff. What else did I talk about here? We did move. You can copy and move. I think I just showed you that. Basically, we did grep is one for searching within a file. This is super powerful. Grep. I get this wrong. NIGTH. Intro text. Oh no, I'm going to get it wrong. Anyway, grep is super powerful. Grep is this really powerful searching thing for searching through text files for patterns. Yeah. Oh yeah, that's what I want to do. So just look at the thing. Got to quote it. GTH intro text. No, I can't remember what's in there. No, anyway, give up. Anyway, grep. You'll use grep, probably. Vim and Emacs, I've shown you these ones. It's like Vim is like famously horrible, like confusing. It's when the first time you use it, you get stuck in it because it's a modal editor. So like you do edits and then you change between modes of how you use this thing. So good thing about Vim or VI, its older predecessor, is it's like on nearly every Unix computer. So if you go onto some weird server, you'll be able to look at a text file with Vim because it'll probably exist. So test.ship. Okay, so this thing here, if I go through, if I just start typing, it won't do anything. If I want to type, I go Shift-I, and then it goes insert, and then I can type, and then I press escape. And then if I want to select, delete. And when you escape, you have to go Shift, quit, question mark, just because it's old. It's really confusing. It's like, I remember the first time I used Vim, I got stuck in it for like half an hour. I couldn't work out how to close it. It's really embarrassing. Anyway, so there's Vim and Emacs is like a holy war of old text editors. Nobody uses that anymore. Piping and redirecting, I showed you a little bit of that. So that's the whole thing. So what you have is these little simple programs and you pipe them and chain them together to make more complicated programs. I showed you that with echo. So I can take echo, pipe it into a text file. You can take the output of one, redirect it into another one. You can make programs with this. So this is just like the outside bit. So my day-to-day, like using Julia or Python or something like that, all starts out with a bash script, where I'll have a bunch of commands in bash that I want to chain one after the other to make a program. Chmod will come up, maybe. Has anyone tried to install Git with SSH? Did anyone bother doing it that way? You did? Did you have to chmod? No, you didn't have to do that. Anyway, changing user permissions. So this will come up like you have, I didn't show, LL is like a bit more detail on LS. So it's listing all the files and folders in here. And it gives the permissions at different levels for who can, like whether it's there's levels of a hierarchy of like who can read, write, and execute that at different levels. So these two shell files, you see that I'm allowed to execute these guys. So if you want to make a shell file, you have to change its permission so you're allowed to do that. That's this thing called chmod. Who am I is useful. Paul Ballett. And sudo is like, if you want admin mode, like you want to do something to a system file, you could do sudo. I'm not going to do that because I'm an idiot and I'll type in my password. This goes on YouTube. That's guaranteed. Again, another useful thing, I've shown you this guy before, is top. I use top all the time to see what's going on. Usually sorting by memory. So we can see what's running. You can see Zoom is hogging a whole CPU and it's using a fair bit of memory. There's a tiny bit in Julia. Firefox here, there's this GNOME shell. Another Julia one, surprisingly. There's two Julias running. Anyone seen this happening on their computer and know what's going on? One's actually in VS Code. So VS Code, I have a Julia plugin for this guy. Has anyone used VS Code and put in the Julia? Yep. that will run a Julia session in there. So if you see two Julias running and you've got one in a REPL, the other one's the one running in VS Code to check your code syntax. Yeah, so that's the task manager top. And if I see one of these guys, like I'm so tempted to do this, I've got this process ID. If I go, I don't like you, what are you doing? It's gone out of control and I want to kill it. I can take that PID, run kill, and it will kill that process. I'm not going to do that with Zoom because then the lecture goes away. Might do it, get tempted, but that's basically kill. Again, if you want to kill a process, it's running and going forever. Some more tools, curl and wget. This is like, yeah, they're two sort of flavors of the same thing. Curl's a big library, wget's like an app. They're for getting data off the internet. I'll show you that in a second. I think SSH is a cryptographic network protocol. So this is, if I want a shell on someone else's computer, I can run SSH. So I do this all the time. SSHing onto another computer on a network or a server to see what's going on. That's super useful. And depending on what you're going to do, there's some compilers, GCC, make will come up again and again, and GDB if you're writing C code and you want to debug it. That's the one. The one I did want to point out though is this test. So what I can do with bash and these bash commands is I can chain a bunch of these guys together and run them all in one little script. So I've got makedir. So from where I am, it will make a directory called test. CD will change directory into test. So I've made a directory test from where I am. Going to jump into that directory. I'm going to make a variable called file name. And file name equals output.txt. Then what I'm going to do is I'm going to run Julia 2 levels down. And there's some Julia program called hello.jl. And I'm going to push that into this variable file name. So if I have this in bash, if I put this little $, it will use that as a variable. Then I'm going to echo, I wrote a file called file name. And if everything works, I can run this and I won't be embarrassed because it will work. Okay, so ls, that was this thing called test. So I go dot test. Oh. Okay, now, what am I doing? No. Where am I? Okay. Why is it not doing it? I'm having a brain fart here. There we go. Why did that? I don't know why that didn't work in my other one. But it said I wrote a file called test, called output.txt. If we look now, there's a folder called test. So if we look at that bash script, it will go make the test, cd into this test, output.txt. So if we go cd test, we can have a look at this guy, ls output.txt, code output.txt. And it says hello from Julia. If we go look at the Julia program, it's basically a one-line Julia program that goes println hello from Julia. So putting all these things into a bash script and running that, that's a typical normal way of chaining all these different programs together. So I don't know what I was doing wrong a second ago. I'll look at this later and go, what the hell was I doing? Anyway, that's a really simple thing. So I want to talk about software and design. Unix is a super, super successful design in software. And it's this thing called the Unix philosophy. The guy who invented pipes came up with this guy, and this is his words. So the idea is this is a good, so this thing's kind of like viral and like it'll live forever. And basically the idea is if you do these things, you'll probably make good software. So they'll be hard to understand now, but it'll make more sense the further you get in. So if you're going to make a program, get it to do one thing and do it well. That's all it does. Like a program does one thing and do it really well and define the interfaces really well. And if you want to do a new thing, build afresh rather than complicate old programs by adding new features. Like every developer should really learn that. Like it's really, really sage advice. Okay, and expect every output from every program to become the input to another as yet unknown program. And don't clutter the output with weird stuff. And avoid stringently column or binary input formats. Don't insist on interactive input. So if you can make a program that another program can run, another program can run that program, it's like it's going to go everywhere really quickly, especially if it's useful. It's really easy to get overcomplicated and you try and make a thing that does all the things. It's like just make little atomic things because you can manage that. And this is like homework advice, right? Try early, ideally within weeks. Like build it really quickly and try it really early. Don't leave it, don't try and design everything up front and then see if it runs at the end. You should be trying to iterate on things. Yep.
What is interactive input?
Have to press yes to go. So like expecting user input to run the program, just like run through. That's what they're talking about there. So like don't expect a human's going to run it, a robot's going to run this thing, and then it will go everywhere. This one's like super duper advice for how you build stuff. Like don't be too precious about things. Throw stuff away and build it again. It should be fun. It's like building sandcastles. You know, you should enjoy it. Just keep making the same thing again and again and get better. Don't worry about it. But really, this one is like, I can't stress this enough, and especially professionally, like if you can turn things around quickly, you can work out, I'm not super clever. I can't work out all the problems up front. It's much easier to do a thing and then see what's wrong with it and then fix that. So like design advice for this stuff. And same with your homework is like, don't think too much, just try and run it, build tests and see if you can pass the tests and just keep going at it until you get better. Use tools in preference to unskilled help to lighten a programming task, even if you have to detour and build the tools and expect to throw some of them out after you finish using them. So this is the thing, as a developer, you're always building tools. Like best developers will like get frustrated with something they're trying to do and build a thing to automate it. And if you're learning software, you know, think of a thing you do repetitively and you don't want to do it again. See if you can make a little script that will run it for you. So think in your life, if you've got a thing and you don't want to do it, how could you automate that? And try and just build that thing because you'll learn really quickly. That's a really good advice. Yeah. Okay. And I won't talk about Git unless anyone has any specific issues. I think just send me a question. I'll talk about it next time. IDE, everyone uses an IDE these days. For the longest time, I'm old again, I just use Vim, like, because you can. Software is just a text, like writing programs, just a text file. You can just use a text editor. Vim with lots of plugins is really powerful. I've kind of switched over these days to using VS Code, and all my knowledge of the old tricks I used to use have gone away, but it's an acronym for an integrated development environment. It's this thing of like, tools make your life easy. So like you can do all this command line stuff. You can use the command line stuff to make tools, or someone else can do it for you. So VS Code is kind of like got a lot of dominance at the moment. Yeah, so it's basically it's just a text file editor and somewhere to run the code, such as a Julia REPL. Then there's like a huge variety of tools. So like someone like in enterprise, lots of people use Java. It's like, it's almost impossible to write Java without a really powerful IDE these days. That's the way the language has gone. It's like you just keep pressing tab and it kind of writes the code for you. It's kind of weird. Yeah, and it's going to get like with these things like large language models and stuff, like as neural networks and stuff get better, it's like, has anyone used Copilot for code yet? No, it's worth a try. It's interesting, like with all the hallucinations and stuff. But basically an IDE though is basically a text editor. You got, these are the kind of things you want. You want source code navigation, syntax highlighting. So this is this useful thing. If I write a Julia program, I get this thing that's like, oh, this is a function and this is a string. And if I look at a more complicated one, you get this nice syntax highlighting. This bit goes blue and this bit, the return goes purple, and you can see all the ends. That's nice to have. Even nicer to have is if it does, like, if it's a bit more clever. The Julia one's not great. I expect it will get better soon, but like telling you when you've done something wrong, like you've got a syntax problem. Like in different languages, particularly statically typed languages, you'll get like, no, you can't do that. Like it'll underline it red and go like, you've tried to do a thing that you're not allowed to do. Before you even run the program, it'll tell you that it's wrong, which is super useful. Code completion is useful. Version control integration. So you notice I ran that little bash script and it's made this output.txt. I'm in a Git repo at the moment. So you've got this little source control thing here. It's saying like, oh, rather than running all the Git stuff, it's like, oh, do you actually want to commit this thing? Like it's got the diffs here coming up. If I click on this guy, it'll come up with the diffs like we just talked about. I can actually edit this one and more stuff will come in. I can delete it and the diffs go away. Cool. That's useful, having source control. And rather than having to memorize all these Git commands, I can just like click the button. It runs the bash commands for me. It mostly gets it right. That's super useful to have. And you can do all the things. You can push, pull, clone, check out, fetch. It gives you all these things that you can do on Git via the command line. You've got little buttons for them if you want to do that. And sometimes it's easier to drive it this way, depending on you. So that having version control integration integrated is super nice. Search is a big deal. So, you know, if I'm in this function, I want to do control find in samples. Okay, it's used there, it's used there, it's used there. I want to go through all I can do a find and replace. Like I don't like that name in samples. I can go num samples and go through and replace them all. I want to do it and not feel too scared that I've done something stupid. And then we go, oh, because it's tracked in version control, it goes like, hey, you've gone through here are the diffs side by side, and you've gone like n samples has changed to num samples, n samples has changed to num samples. Is that what you want to do? Having all this stuff, and if you want to search through all the files, Control-Shift-F. Do I have this anywhere else? No, I don't. That's fine. I only have num samples. Cool, and there's all the instances. If I want to click through the folder and go like, oh, there's that one, blah, 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 blah. Language support, and this in code linting, has anyone come across this before? Code linting is like a way to catch bugs by not catching bugs, by looking for terrible bits of code. So it's like there's like a correlation. It's not causal, but if you've done something weird, like you've written a function that's like 800 characters long in one line, it'll go like, that's probably crap, dude, like stop it. And it will complain. So this idea of code linting, it'll go through and go like, you know, look for things that are like indicative of stuff going wrong, but not actually detecting stuff going wrong. So that's kind of actually a good thing to run. A little bit prescriptive. Recommend VS Code because it's kind of dominant. Again, these things always change. So like a little while ago, everyone was using Atom, but then they think it was too slow, whatever the next thing is. There's a whole bunch of proprietary ones that are amazing. Like if you go work in a company, they'll be really, really good depending on the language you're using. Has anyone got experience with any of these? Like any Python developers? What's everyone used for Python in the past? Just Notepad or? Yep, that's right. IntelliJ is really good. Yep. JetBrains is good. All the JetBrains stuff is good. Yep. Cool. That's a bit, yeah, for this stuff with Julia, for where it at, VS Code is pretty simple. It's open source and it's free, so that's cool. It's open source by Microsoft, which goes into the next bit, which is like, for someone of my era, that's kind of like, hurts my brain a little bit. It's like, doesn't make sense. Those two words together. So software licensing is a thing. And again, for you guys, nothing to worry about. Your students, you're not trying to make money off this stuff. Problems come out when you're trying to get attribution. So if you decide to release your stuff into the world, you have to care about the provenance of all the stuff you're built upon, like where it came from, what they wanted you to do with that code. It's kind of annoying to have to worry about it. We recently went through this at my work. Plot Logic. I have my drink bottle from work. We had to go through all our code base and work out if we had any GPL code in there, because we're a commercial operation and GPL has some restrictions. So it's actually fine for me. So that was good, because I thought too much about software licensing. It's nothing to be scared of. Like, I remember when I first went out in my career, I was kind of like worried about doing the wrong thing. Like, I was going to get personally sued or something. Like, if I'd accidentally gotten some code and included in mine that the licensing agreements were, it doesn't really work like that. It's more like your company is going to get in trouble and you'll probably lose your job, which is like a second order problem, but it's like, it's not the same as getting sued yourself. But it's like, it's pretty easy. It's like, they're not actually that bad, like what happens. So there's two big classes of proprietary software and free and open source software. These two things are different things, but proprietary software is just like, yeah, no, it's commercial stuff. You're never going to see it. Like, if you see it, someone accidentally pushed it to GitHub and put it into the wrong repo, and they're going to get in trouble in a little bit. That's like most of the work I've done in my life is proprietary software. All the software I write, it's like behind a lock and key. Nobody's ever going to let you look at that stuff unless you work there. And even in where I work currently, the stuff I work on, only a small group of people are allowed to look at that because it's sensitive IP. So not everyone in the company is allowed to look at that software. You can have levels of trust. That's what happens. It's kind of bizarre for me because I don't think that way, but it's the kind of thing you have to worry about when you're running a company. The other big class, open source proprietary software. If you get your hands on that, just delete it. Don't even look at it. Unauthorized use you're going to be in trouble. Severe legal consequences for that one. Free and open source doesn't mean you can use it however you want, though. There's lots of philosophies around this, and it depends on the person who wrote it. So, like, all code is written by people. Like, it's all kind of at some level respect for the person who made it. So even though I find certain things like GPL annoying, it's like, I got to respect that I didn't make that thing, and like they put a lot of time into it. That's how they wished it to be used. So I probably should respect that. There's three broad classes though, which you should know about. There's permissive, copyleft, and public domain. Permissive is kind of like the one that won. Like most things, like you'll see Julia, so like the default license when you go into GitHub, it'll say like, do you want BSD equals 3 or MIT or Apache? Because that kind of like is permissive. If I write this thing and I open source it, someone commercial wants to use it, knock yourself out. If I want to use it in another open source project, knock yourself out. It's like, I don't care. Copyleft, on the other hand, is a bit more aggressively viral. The whole idea was if you use GPL and you have a derived work on top of the GPL work, your work is also GPL now. So this is why companies are scared of it, because like if you pull in some GPL code and you build something on top of that, it's considered derived work. And so somebody asks, if you try and distribute this code to a customer and they go, hey, I'd really like the source code for that. You're like, yep, okay, there you go. You have to give it to them. So that's actually the consequences. Like if you have a derived work on GPL, your work is GPL too. If they want the source code, anyone who gets your program wants the source code, you have to give it to them. And this happens sometimes. It happened for a car company not too long ago. Their infotainment system was based on the GPL, and someone noticed and they went, hey, love all that source code, and they had to give it to them. It's kind of funny. Creative Commons is public domain, which is like, yeah, whatever, don't even care. Don't even care about attribution, just use it, right? That's public domain. Rough summary, I'm not a lawyer. Permissive licenses are favorable for commercial use of derived software. They're free to redistribute, but they must also be copyleft work. And public domain are most free and can be used as desired. So public domain is like, yeah, whatever. If you don't follow the rules, though, you can get in lots of trouble. And there's lots and lots of legal cases. And they tend to be between companies. They're not like smashing an individual developer. Basically, if you're an individual developer, you'll get like a cease and desist, like, please stop releasing that code or make it GPL, or you won't go to jail or anything terrible. It's like not like that. But it's multi-billion-dollar cases between big companies suing each other. And the other cases is typical way of, so your employer will care a lot more about it than you will. So you sort of have to care about it. Examples, proprietary, Windows, Mac OS. Mac OS, I said, even though we looked at this thing and, it's got a history from Unix itself. Now it's proprietary, so I don't know how that works. Probably because they were public domain originally. MATLAB is another one that's proprietary. Permissive, Julia, Python has the Python Software Foundation license. Android is an interesting one. I said about that because it's Linux for the kernel, but the user space stuff is Apache, so that's permissive. So all the stuff running on top of the kernel stuff itself is GPL. Copyleft Linux itself and R, they're both GPL code. There'll be some other ones like Qt if anyone does any plotting. Yep.
Yeah, so thinking of the stuff like how is it you can download a file like a game and run it on your computer, but you can't access the source code. Like,
Yeah.
so, like you have the source code, like it's right there.
Oh, you can decompile it.
Right.
It's compiled usually. Like if it's someone's written a game in Python or Julia, it's like, yeah, cool. You kind of got the source code if you're running it locally. That's kind of, it's this funny world we live in where you run stuff on a server and you just serve the results to someone. It's the usual way they'll get around that. So like where I work is like we do all that stuff, Python, Julia, these kind of higher level languages, and we will run it on a server and we don't actually give it to the customer, we give them the results. So they give us the inputs, we give them the results. All our code sits on a secure server so they can never get at it. Yeah, in your case, so yeah, and you can decompile it and there's lots of legal stuff around that and whether that's okay, and reverse engineering, not my area. It's a bit of a gray area, I think. Yeah, anyone, you get a talented developer, they can decompile and work back out what you had for most compiled languages. So they'll do source code obfuscation. They'll run something that kind of makes all the variables terrible. So it looks like, someone learning the language wrote it and they'll mess with it that way. So there's all these tricks, like even JavaScript, like will run in your browser and you can expect the source. Like everyone, hope you've all seen that. Like if I click on here and I go like, you've got like tools, web developer tools. I can go here and I can go like, oh, there's some JavaScript in here. I can go to console and see what's getting put out. I want to click on a thing, I can work it out. There's not much going on here for this one because there's not any JavaScript running in the browser, but that's the thing. Like you can get the code that's running on your web page if you want to. Kind of wild time to be alive. Yeah, public domain, BLAS and SQLite, I think are public domain. They're an example of that. Any questions on that? I think it's important to learn about it because I think I never got told about this until I started working. So I think it's useful to know beforehand. Don't be scared of it. There was a lot of kind of an older school thing to be a bit more scared of this stuff. There was lots of scary legal cases, like Microsoft was pretty aggressive back in the early days. Cool. Unit 3, get onto it. Okay, so quickly, yeah, we're going to deal, this first little bit of Unit 3 is going to be about data, and I think I've got a little bit about plotting as well. So that's cool, I'm not lying. Then this is we don't have much time for this in this course, but it's kind of like a bit me with my background I'm super interested in. I think it's really, really interesting stuff about numerics and numerical algorithms. Like things like differential equations and integration and numerical linear algebra is like stuff I love. I think it's fascinating. Lots of interesting things of this intersection of like trying to do the pure maths thing, but get it to run in a computer with its limitations, and also, yeah, modeling physical things. Like I'm not a pure mathematician because I was always interested in applications, always on that intersection of being a physicist and applied mathematician because I like, real things and understanding how things work. There's other courses you guys can do that'll be much more detailed, just good taste. And also you'll get a bit more on data. So everything here is going to be really quick and superficial. Yeah, particularly the big takeaway point from this section will be floating point being slightly weird and doing weird things. If you can come out of this part of this course and take one thing away, it would just be floating point is a little bit strange. It's like pretending to be real numbers, but it's got some strange properties that you need to keep in mind. Much like we had the uints and ints, and they have this weird, they'll flicker it back around from the bottom because of the limitations of modeling it in a fixed precision format. You have the same thing for real numbers and they're modeled as floating point. I there's an example here that literally every 6 months comes up in my professional career. It's still like, it's like, I need to remember this thing. So I always have it in this course because it's like, this bites me literally every 6 months. It'll come back again and again. I was like, oh, that guy again. Yeah, deal with my data. So again, what's a file? I remember being confused by this stuff. It's just a collection of bytes stored on your operating system or disk. These files, that's all they are. So text file is just bytes with a particular encoding. So we'll just do this guy. So again, this is very similar to the demo I gave before. We're going to echo 1, 2, 3, 4, 5 with a new line into myfile.txt. ls, we've got two things in here. If you want to launch VS Code from a terminal, you just type code, myfile.txt, 1, 2, 3, 4. That's ASCII encoded. So it knows that this is just a bunch of bytes again. So ASCII encoding, we did that back forever ago. This browser knows, this code editor knows to interpret this as a text file and can display the ASCII characters. But you can get more raw stuff than that. Yeah, again, I said, here's one of these things. I think I did this via requests before. I'm going to make this a bit wider so we can fit it in without it running over too outrageously. So curl is a command line tool for getting stuff off the web. I'm going to download into a file called shakespeare.txt from that web page. Before I did that with requests and JSON, I did it via the Julia tools. You can do the same thing via command line. Cool, downloaded 5 mega stuff into a file called shakespeare.txt. So if I go code, I was trying to look at this in, Zoom, go away. I was trying to look at this in Julia and it was disgusting, but if you just get it into a text file, it's kind of easy. So this is the 100th e-text file presented by Project Gutenberg, blah, blah, blah. You've got a text file with new lines and stuff, and it's got lots of Shakespeare in there. Cool. Again, we had those Unix. If you want to just see what the top is without opening it in the text editor, you can get the head. It'll give you the top 10 lines. Tail, Shakespeare.txt will say at the bottom. You see we just talked about licenses. It's got some legal stuff, scary legal stuff down the bottom about what you're allowed to use it for. Applies to data as well, which is kind of an interesting thing. Yeah, so if it's encoded as a text file, you can open it in an editor and it will make sense of it. Otherwise, it's binary and you're not. So let's make some weird binary file in Julia. So we'll go here, Julia. I'm going to file equals open. I'm going to open a file called mybinaryfile.dat, and I'm going to write into it. Cool. That gives me this type called an IO stream, and I'm going to write some int 8s into this guy from 1 to 20. So hopefully you're all fluent enough in Julia that I don't have to go through. So I'm broadcasting int 8 over this collection this iterator 1 to 20, and I'm going to write that into file. Cool. So it wrote 20 bytes into that file, and because of file handling stuff, I have to close this file. Cool. So I think that was in test. ls, so there's this mybinaryfile.dat. If I go code mybinaryfile.dat, what's that junk? It doesn't know what that is because it's not a text file. Again, this is just bytes. If I interpret it as a text file, it's got no idea what it is because they're int 8s, right? So, however, yeah, you can do this thing called hex dump. I don't have the hex dump thing. I think I have it here. Again, I have hex dump here. I have it as a command line thing. I don't know if it's a plugin. mybinaryfile.dat. Cool. So in hexadecimal, you can go through this thing and go, cool, what are they? That's nice. This is the thing you were asking about. If you got some arbitrary thing and you go like, oh, cool, what is it? I want to go and poke around and find out their secrets. You can do a hex dump, run strings on it, whatever. There's a whole bunch of tools. You kind of have to be a bit clever and guess data types though. So you tend to look for patterns in the binary data to go like, oh, that looks like a uint 32. Well, that looks like a float 64. And if I read it as a float 64, oh, it's 12.3. I can understand what that is. So I have friends who like do this as a hobby, decompiling stuff. They're really nerdy people, but they love it. Yeah, I've just like get some random binary format and then work out what it is. So most things like, all these files like a JPEG or an MP3, they're just binary formats with some special encoding, depending on the data. Yeah, that's it. So I think that's pretty much where I'm at. I've got like 1 minute to go. So that's all the files you see, JPEGs, PNGs, they're all just different encodings of bytes. That's all they are. So the encoding tells you how to read it. If you want to read it, you have this special interpretation. Some of them will be hidden. They don't want you to find out what the binary encoding is. So if you get a proprietary data format, so what would be an example of that you would have seen? Think of that one. Has anyone, maybe it's easier the other way. Is there some weird file format? Like maybe Excel. What's an Excel data format? Is anyone like an Excel sheet? If you save that, what do you think it is? Anyone got any ideas? Yep.
Well, I think it's just a zip.
It is a zip. It's a zip of this thing called XML, which is a thing like JSON. So that's a less hidden version of it. But I've got things in my professional career where, like, say, some hardware vendor makes a particular type of sensor, and they don't want me to read the raw data myself. They want me to use their software to read the data so they can sell two things. They'll hide the data format, they'll encrypt it. So if you want to read it, you have to decrypt it to get the data format back out. Really common thing. Proprietary data formats are a thing. Really common one you'll see is JSON, and this will come up in your homework. Has anyone had fun digging around through JSON? You enjoying yourself with it? No? It's all right. It's pretty straightforward. We're going to talk about both of those in the next time. CSVs and JSON. CSVs are the main one. So this, basically because of the predominance of Excel, this tabular data format is a really useful way of viewing data and thinking about data. Scientific data is often tabular data, and this is kind of like the de facto, and it's kind of terrible in lots of ways. But, you can't win against I'd say, like, in an interesting way, Excel is the most successful programming language. Like, nearly everyone has a copy of it, and nearly everyone knows how to use it, which is kind of interesting, and it's Turing complete these days as well. So go figure. Yeah, so we'll talk about, I think I'll do that next time. I think this is a good time to stop. We've just started Unit 3. We'll talk about CSV files and how they're encoded. Any questions on this stuff for tonight? No, thank you very much. See you tomorrow.